and also the HPC Achievement Award in 2021 for her trajectory. Rosa has a privileged view of workflow applications and systems, which are crucial nowadays in the field of data science and artificial intelligence. Today, she is going to discuss this topic, the convergence of HPC, data analytics, and AI through workflow methodologies, which we believe can be of great value for ADBIS attendees. So the floor is yours, Rosa. Thank you again for being here.
Thank you, Anna, for the introduction, and Oscar and all organizers for inviting me to give this keynote. It's a pleasure for me for being here. So in my talk, I will cover on one side an overview of this project, which has been very important for me because I'm the IP of this project that has involved a large number of partners, and I think we have been doing good contributions. Okay, but I also include in the last part more details about the research that my group does. Okay, to see if any of you see possibilities of collaborations and contributions to what we do. Okay. So a little bit the motivation when we were deciding to make this project is because I was involved in a series of international meetings called the BDEC with data and extreme scale computing. This extreme scale is because at that time we were looking into the exascale systems, the 10 to 18 flops systems. Okay. And there was a lot of discussion, both with people coming from the HPC side and more from the big data, and also lastly also from AI part, about how the processes were done in the environment of HPC. No? And while most of the applications that are run in HPC systems require a large amount of data, no, that can be get from observations from instruments, from data that exists, records, etc. And there are some processes to prepare this data, no? And the acquisition, filtering, or generating the data that is then that fits the simulations and modeling that is typically done in HPC. And later there is another analytics phase where you will process the data to make deductions, to predict. And probably there is a loop here, no? So you will repeat these phases. Although this can be seen as a single process, in fact, was implemented at separate stages. No? And what is more, using different programming models, using different tools, even different environments. No? Probably what we wanted to see was, okay, can we do this type of processes into single workflows? How can we integrate these different processes, these different type of models into one? No? The other aspects that were taken into account is the complexity of the infrastructures. Infrastructures, if we think of the cloud or HPC system, can be seen as a standalone. But in fact, every time more people is talking about the computing continuum in the sense that we will have data that comes from sensors, IoT devices, in the street, in the cars, big instruments, that get the data. Okay, then we can have edge devices that start to process or even do learning process, whatever, in the edge. Then there are some other fog devices, and then more the large scale systems, HPC, the supercomputers, the cloud, and nowadays also is starting to add also the quantum system. But the other thing was how we can orchestrate this complex infrastructure, but taking it also into account that the applications are every time more complex. No? The demand of the developers, of the scientists, is every time higher, no? When you speak to them. And then another thing that we wanted to do is to, when we were composing these workflows, to be able to adapt dynamicity to them. No? And dynamicity in the sense that there will be data that will be streamed from the data sources, and then here we can have a dynamic workflow, not that everything is predefined, and I will do this step, but this other. That there can be room for exceptions, no? Saying, okay, I'm analyzing this space area, but I'm not finding what I want, and I want dynamically to be able to say, let's change a little bit the input parameters of the simulations or the data that I need, and do another process. No? and at the same time integrating everything with data analytics, workflows, and aspects of artificial intelligence. And not only in the HPC environment, no? Some of these can be run in cloud environments also. This includes what I was saying before, no? The integration of the different infrastructures altogether. No? And more recently, what we were also looking into when we prepared the project is about the fact that using an HPC site is not that easy. Okay, it's complex for the user because, for example, when you need to install an application as a user in a community, you would need first to develop the application, okay, and perform, in principle, a manual deployment, even yourself as a developer or through the help of system administrators. And after this, the users can use the application, and if we have to use another HPC site, this process again will be manual, etc. No? Or if you want to use the cloud, the same. No? So our motivation was, okay, we see in the cloud and in other environments paradigms like the function as a service, where using the applications is much more simpler. No? So our goal was saying, okay, can we design and implement something similar like the function as a service, but for complex workflows that run in HPC systems? No? And a bit the idea would be, okay, I have the workflow developer, but then I register my workflow, and this can be more simply deployed in the HPC system. And if I need to run in another HPC system, this process can be somehow automatic without requiring this manual usage, and also offering an interface to the end users that looks more like as a service, the as a service framework. Okay, so with this we make this proposal, the flows for HPC, which the main goals is to offer development and execution tools that combine different aspects of HPC, data analytics, and AI in a single workflow that support this dynamicity, reactivity in the workflows, and that we not only deal with the development, but also with the deployment, with the full life cycle management of the workflow. I'm offering this idea of the HPC workflows as a service. In addition, we added 3 application pillars on different areas of research, on engineering, on climate, and on urgent computing for hazards. And in addition, trying to make a connection with the centers of excellence here in Europe that are specific communities. It's a type of project that the HPC area has that tries to serve the communities of that type of application. No? Like Accelerate is for manufacturing, ADBIS is for the climate, and the CHIS Center of Excellence is for urgent computing. Finally, we are doing in the project some optimizations, some architectural optimizations for specific architectures like GPUs, FPGAs, or the European processor. So a little bit, what will be the outline of the rest of the talk? I would like to explain a little bit better what the pillars doing, okay? And a little bit the architecture and methodologies of the project, and how we implement them with top-level workflows and this aspect of the HPC-ready containers to help on the easy deployment. So this will be more the project-oriented. In this project, then you are using some of these components that are contributed by my group, but I wanted to separate it a little bit so you can see what is part of the project, which other project partners contribute, and what is the contribution from our group. Okay? And then I will present a little bit more PyComs, which is a programming model or workflow development environment that we developed in my group. That is LEAP, which is a machine learning library, and the distributed data set, which is a set of methods and a data structure following the Spark-like programming model. Okay? But all of them, these 2 are built on top of PyComs. Okay? And then I will conclude the talk. So a little bit what are the application pillars in the flows for HPC. We have this manufacturing pillar that the end user application comes from Siemens in Germany, where they have big engines in mills, in industry that are electrical and don't have any explicit cooling, but the cooling is by itself by the rotation of the engine. Okay, so it's air cooled by itself. No? And these engines, of course, if the temperature increases, they can be damaged. No? So they try to model the cooling of these engines in a way that they can better monitor and steer their functioning. No? And to model these engines, we have very fine-grained simulations in HPC that involve a large amount of computing. Okay? But the idea is, can we generate an AI model based on this large campaign of simulations and reduce the model with other model techniques and generate a smaller model that can be deployed in the edge, close to the engine, or in the cloud? Okay? So a bit is what this pillar is trying to solve. No? This can go through different iterations, no? Like maybe the first model is not accurate enough, so then you need to run again some more simulations, okay, generate new input data until the model is fine enough. So this is one of the aspects that, according to them, can have a large impact in this in the area of industry, or in the industry 4.0 vision. Okay. Other workflows come from the climate area. For example, is another community that are eager of using HPC. No? And for example, they have these system model simulations that perform large number of simulations that are computationally very expensive. No? And not always, maybe all simulations will lead into contributing to real significant information. No? So a little bit, the approach has been, can we improve dynamically the results of these workflows by dynamically deciding which simulations will not give an additional contribution to the results and being able to prune them dynamically. So a little bit this is what I'm doing, and in addition, there is a part of the workshop that the workflow, that will use the results of these simulations, and with AI techniques based on convolutional neural networks, perform predictions of tropical cyclones, especially in the area of the North Pacific. The other pillar is dealing with urgent computing for natural hazards, in particular for earthquakes and their subsequent tsunamis. Okay? And basically, these workflows have a very similar pattern. In the occurrence of an event, a large number of sample data is generated, input parameters, that are used to launch a large number of HPC simulations, sometimes with redundancy. So sometimes the same simulation for ensuring that the results are getting faster or that are sent in duplication, redundancy to multiple HPC sites. And then there is an amount of data that needs to be post-processed and generated. So then they have been working on performing integrated workflows of this type of workflows, because in this case the community was a little bit behind on having integrated workflows with all the steps integrated in a single application. No? So one contribution has been this, and the other is that they have enhanced the AI and data processing tools that they are using to generate impact maps and other type of mapping. No? And they're working on the areas of Mediterranean basin, Mexico as well, and Iceland and Chile, which some of them have scenarios of earthquakes only, others they have scenarios of earthquakes plus tsunami. Okay? And they're really contributing to the areas, not only the technical aspect. No? Okay, so with them we worked in a first phase on collecting requirements from the applications that help on the design of the flows for HPC architecture, together with components that were contributed from the partners in the project. No? And we designed the architecture that has 3 different layers. Okay? One is for the definition of the workflow, where I will give a little bit more of detail in the next slides, how we do it. Then there is the definition of this HPC Workflows as a Service interface, but also a set of catalogs, repositories, where we can have the different components of the workflows and the workflows themselves, as well as models from AI, available for reuse and reproducibility. Is another aspect that has been taken into account. And then we have a layer where we have the different elements for efficient distributed execution, both in the area of the runtimes that are needed, but also for the data management or specific libraries like Data Clay, which is mainly contributed by the group of Anna, on management of persistent data that is used in the application. And with regard to the software stack deployment of these different components, are not all of them deployed in HPC systems. No? This is one thing that also we discussed at the beginning, is that the HPC environments usually have very strong policies on the access. For example, from inside the computing nodes, you cannot access outside, and providing services, as we know, like web services or the paradigm as a service in an HPC system is very difficult. No? That's why we did an analysis of which of these components could be hosted in the HPC environment and which will have to be in a cloud, no? And we call it here the gateway infrastructure. No? So as you see, the different repositories and itself the HPC Workflows as a Service interface and other components are hosted outside the HPC infrastructure, no? In a cloud space on OpenStack. And then the other components can be hosted in the HPC system. This was also an interesting discussion with the partners, because that is when you realize that these policies from the HPC operation really impact on how you implement things. Okay? So then going a little bit on the development of the workflows, we have these components where we have software that is available, like simulators or tools for data analytics or AI, etc. And then we have the data catalog that also stores data sources that can be from other executions or can be links with metadata to existing data sets. Okay? And with this, there is a developer that is able to compose a workflow. No? For composing the workflow, we differentiate 3 different parts. One is the more computational intensive part, the PyCom's code, that I will explain a little bit more later, no? How we develop computational workflows with PyComs. Okay? That is the part that runs inside the HPC. Okay? But then we have also data aspects, like bringing the data sets from outside in repositories or in the cloud to the HPC, that are described with data logistic pipelines as a separate part of the workflow itself. No? And finally, we have a top level definition of the whole workflow in Tosca. This is a standard that has been highly used in the cloud environment, that defines how these different components are integrated together. Once we have the workflow, we store it in the workflow registry, and using LM4 Cloud interface, we can deploy it in the HPC. Now, this provides an endpoint to the users that can invoke the application using the HPC Workflows as a Service API. A little bit about the data catalog and the services for data. We have on one side this data catalog that is provided as a service. This lists the data sets. That can be just data sets that are there because we added, or they can be automatically added when executed in a workflow. Even intermediate data sets can be stored there, or the final data sets. Other types of data that can be added here is the containers that we need for the deployment. It's a part of the data set in the sense that we need to move it from an outside repository to the HPC for the deployment. And then we have the data pipelines. Data pipeline is how we want to move the data. In this case, they are programmed with Apache Arrow, okay? And they define, for example, the simpler case will be that the workflow have an stage in, and we move some input data sets into the HPC system, then we do the computation, and then the stage out. This would be the simpler case, but can be also, we add also the aspects of the transferring the container images, and also it can be cases where you require temporary transfers from outside to inside HPC, or saving some intermediate results in the data storage that can be also programmed with this data pipelines. And then you have the data logistics service, which is the actual service that executes this data pipeline. So it's the engine that is able to interpret this function and performs the data movements. Both the data catalog and the data logistics services are available with corresponding endpoints. So then, how we then develop the top level approach? I will try to explain a little bit this idea. So we have on one side, for the general management of the workflow, we use Tosca. And with Tosca, basically, we define the model of how these top level components of the workflow, how they interact with it there. When we have this Tosca component that will be stored in the workflow repository, we can use the HPC Workflows as a Service API to do two things. One is to deploy their workflow using containers, and the other is for the execution with HPC Workflows as a Service API. For the deployment, we use the Alien for Cloud, which is a portal provided by Atos that helps on this. But then for the execution, we have a specific API, REST API that has been defined for the execution. So this example will be one case of a workflow defined in Tosca. Each of the boxes represent one step of the workflow. And we have also a component that describes the HPC side, the characteristics where you want to execute this workflow. Okay? Then we have one phase that will be the installation, where you have one step for the image creation and one step with the data logistic service to move the data image, the container image, into the HPC. And then we have the execution, when, for example, we have one step of staging the data from outside, the PyCom job that performs the computational part, and another component that performs the stage out. So when we want to perform the image creation, we also were discussing a little bit about this creation of images, because one aspect that we realize is that if you get the regular containers that are available in Docker repositories or other generic repositories with images that are already made, they are very simple to use, and they are also compatible with different hardware. But if you want to run it in an HPC system that have a specific architectures or are using a specific libraries for the parallel programming models or other aspects, they will not leverage the potential of the HPC system. That's why we said, okay, can we improve this? And there are methodologies based on the Buildex. Buildex is another component of Docker, but that enables creation across compilation image. This means an image that you create in a regular architecture like Intel-based, but can be compiled for like a Power 9, which is a specific HPC architecture, or for other specific architecture, and can also take into account specific libraries or the architecture like the GPU that is used in this system. So you can do this manually, but what happens if you want to do it automatically? And this is what we've been working in the project with. This, we call it the container image creation service that tries to automate this idea. And which information we use? We use part of the information that are available on these repositories that I was telling you, like the software catalog, where we will have for the different components that are used in the workflows, information of how to build these packages, for example, using the Spark methodology. That is one of the ways that you can automate the installation of software. we will have the receipts of how to build this software. And also in the workflow registry, we have the information of the components that are needed, for example, for a specific workflow or for a specific workflow step. No? For example, here in the pillar 1 case, that is this one that we are showing, okay, here's pillar 3, but in fact this is for pillar 1. We use COMS as a generic tool for the workflow. We use the DISLEAD for the machine learning, and we use Kratos for the simulation of the HPC bar. No? And then we have a service request that basically specifies the details about the architecture for which we want to generate the image, and information about the libraries that we want to use. Okay? And then information on how to index these registries and catalog to get the required information. With this, we can build containers that are specific for this architecture and for this software. And we have done some, I will not go into all the details of the results, but the important thing here is we have done this for applications from the 3 pillars. This is for the pillar 1, pillar 2, pillar 3. And we have experimented in 2 different architectures for these general purpose processors applications. This one is using GPUs, that's why we only have one architecture we have run this. Important is this is what you get with native installation, okay, doing by hand. This is how you get it if you done it with generic containers, with containers that have not been optimized. And this is what you obtain if you use the HPC ready containers, this service that we have been developed. You can see that here, these bars are basically, this is time, okay, so less is better. Here, between the native and with the HPC ready container, basically, we have the same time. The difference is not with the eyes we cannot see, but we see here difference. No? You see that the reduction, in some cases, is even, although it doesn't seem, is twice faster with the HPC ready containers, or some, in this case, 40%. In this case, the difference is not that big, because most of the execution of this solver is done in the GPU, and the application is already optimized. Okay, so making the specific container, in this case, we will not win. No? But in general, is an excellent contribution. Okay? So once we have the container, okay, it can be invoked through the Alien for Cloud automatically. The workflows can have 2 different parts. No? The deployment, no? Basically the user through this Alien for Cloud portal will invoke the part of the Tosca workflow that invokes first the image creation, that is what we just saw, and then the image movement with the data logistics service to deploy the workflow. And with this, we have the workflow available for execution. The next step is authorizing the user. No? In an HPC system, you cannot simply invoke with a generic user. Each of the users required to have an account on that system, because if not, this breaks the policies of the centers, and these are things that we need to respect. So here you can then also, using again the Alien for Cloud portal, you can authorize the users or a group of users that can execute this work. And then for execution, the user can use the endpoint that is provided after the deployment through the HPC Workflows as a Service API to invoke the execution of the workflow. And then this, for example, can invoke different stages, like using the data logistics service for the execution of the staging, the execution of a PyComs workflow using PyComs, okay, and the data stage. So this will be the top level, and until now, most of the things that we've been doing in the project. And now is this second part of the project where I want to focus a little bit more on what my group does, okay, and also a little bit of what we have contributed in the project, but it's a little bit more focusing on what we do. So what is PyComs? No? PyComs is a task-based programming model or workflow development environment, depending on what you want to define as, where given a sequential application, we identify parts of the application that are annotated as tasks. No? And what is a task? Well, task in general in Python, in this case, I'm showing the case of Python, is a method that have predefined inputs and outputs, and we identify it as a unit for computation. Okay? And important is also that we define the directionality of the data. If data is read, it's an input, or if data is written, or if it's written, which will be this case, but is an in-out. Why we want this information? Because what we want is to identify the potential parallelism of this sequential application. Okay? And we do this at the task level. No? So when we execute the application with these annotations, we build a task graph that represents the application. Each of the nodes in the graph represent one task. Okay? So every time we call a function that is annotated as a method, as a task, we add a node in the task graph, and we add edges between them if there is a data dependence between them. That's mean this second task here is reading one result of the previous task. Therefore, it cannot be run before this task finishes. Here we have some tasks that, these green tasks that can run in parallel between them. Why? Because although they have some input parameters between them, there is no data dependencies. No? And then between them, these tasks can run in parallel. Okay? And here we have other serial tasks. Not here between them is a chain of tasks that depend one on the other. But overall, we have plenty of parallelism in this area of the task graph that allows us to run part of this workflow in parallel. Okay? So this is the main idea of this task parallelism. It's not only in us. We were proposing this many years ago, and we have implemented in different frameworks of these programming models, and others are using as well. One of the aspects that I think is that is more differentiated from others is that in our case, this task can be inside, can be sequential code, just pure Python, or can be parallel using threads or using other types of parallelism like MPI. So we compose the task parallelism with other means of parallelism, like thread level, OpenMP, MPI, etc. Another aspect is how we deal with the data. No? The data in HPC or in a cloud, you will have different nodes, and the data in memory are in different spaces. And as well as the storage, we will have different nodes. In HPC, sometimes you have a file share system, sorry. But in general, also you can have distributed file systems. So the runtime is also able to deal with this, offering to the end user the illusion that there is a single larger memory system or a simple single file system. No? So we deal with all the required data transfers. If data that is used in this task has been generated in another node, we will take care of moving this to the other node in order to have it available for execution. And in general, it can run in clusters, HPC clusters, in clouds, and well, I differentiate here the fact that we can also deal with clusters that are managed with containers. I will not go into all the details of the syntax, but I wanted to show that in principle, annotating can be very simple. Here for AIB, we don't say nothing because by default, if we don't say nothing, it's that there are inputs. Okay. We also take into account if the method is returning any value. Okay. Then we have a smaller API for data synchronization, where we wait, in this case, for all the tasks to finish, or you can wait for a specific value to be generated. Okay. But I wanted to highlight other annotations, other decorators that we have. For example, the constraint is very interesting, I think. Is that you can say to a task that has a minimum requirement on the amount of memory that you need, for example, or on the number of threads that is using, or other constraints. No, you can define here the requirements. Can be most of them can be hardware, but can be also software requirements that this task requires. And this helps the scheduler. These are hints to the scheduler in order to decide which task to place in each node, how many tasks we can place in a node, for example. And then we have other extensions to link with other programming models. MPI is one of the main programming models using in HPC environment that deals with parallel processes, okay, that are communicated through messages. In this case, This method that I'm indicating here is an external library that is implemented with ADBIS. No? But I would like to have in my workflow invocations to this external simulation, this HPC simulation. This is the way we are linking with this. And then we have also an extension to deal with individual failures of the tasks. No? Workflow can have a large number of tasks. No? And an initial design decision that we made is to say, okay, if there is a failure, we will stop everything very safely, no? And we stop the workflow. But then speaking to some users, in this case was from life science, I said, well, if I'm trying 1,000 omics simulation, I don't care if a few of them fail. I just want the workflow to carry on and give the results. No? So you can define this. No? On failure, what to do? Just ignore that the task has finished. Even to say, oh, I have some successors, so if I fail, ignore that I have failed, but also cancel my successors and other aspects. No? And this has also impact effects on how we have to manage the files. For example, if this was generating an output that gives a result, and then later I have a reduction on all the results, I need maybe to generate a file even it's empty, because if not, when the reduction function arrives, if it is missing some data, it will also fail, no? Because of missing this data. We have done also support for data streams. In this case, the basic implementation we have is based on Kafka. So now a task can have inputs or outputs that are streams of data. These streams can be data that comes from a camera or from any source of streaming data. Or it can be, for example, we have use cases of MPI applications that are generated intermediate results, no, through the different iterations, and that we want this to read it. No? It can be also monitored as if it was a stream. No? These are interesting cases that we have found. So we have done also this extension. And here, important thing is that then we have different type of tasks, because the tasks that you do with data flow, no, with the streams, can be seen as services, no, that are alive during the whole application, okay, and are receiving data through these streams. No? And it is different how traditional tasks work, that are tasks that receive some input data, one operation, and finish. So the paradigm changes also. Okay, so then this is, besides the syntax, we have this runtime that supports this functionality. At execution time is deployed as a master worker. So we have one master that runs the runtime, which has different components for scheduling, for resource management, whatever, and has also the binding to different languages. Right now we support Java, which is native. The runtime is in Java. Python support and C support. And then of course different tools for monitoring, etc., and to manage the application. So this is hosted in the master, and then the worker at the beginning was very simple. With the time has evolved into a little bit more complicated, but still compared with the runtime, is a simple component. Okay? And the workers receive scheduling decisions from the master that they need to execute the task, they need to perform an operation with data, whatever. We have support for elasticity. In the cloud, this is relatively easy, because in the cloud you can add new images, start new images and run them. In HPC, it's a little bit more tricky, because you have to interact with the job scheduler to add new nodes to the execution. Okay? And other things that we are supporting is task nesting, so tasks that are inside other tasks, no? That's the hierarchy of tasks. And we have, as is mentioned here, monitoring, no? How the workflow is progressing, or generation of trace files that are a post-mortem representation of the execution of the application. We have also recently added provenance. This is based on a specification that is called ROCRATE. Okay? Basically, it records the accesses to the data, the files that are used, and also the software. And this creates this object, raw object, okay, RO object, that can then be uploaded to a repository. For example, we are using the workflow hub that is used a lot by the life science community. to upload provenance objects of our workflow that can then be used for reproducibility, or just for looking at it, whatever. Okay, so then in the project, we have been working on some extensions to integrate more the aspects of data analytics and artificial intelligence with what was at that moment the PyComs environment. So what we are looking into is, this will be the basic type of workflow that we want to be able to execute, where we have some parts that are HPC software, some parts that can be data analytic processes, and some parts that can be artificial intelligence. Maybe not all of them, but or a combination. No? And also an observation when working with the pillars is that in some cases, you will have that between one step and the other, you require a data transformation. Here we are defining a data transformation, for example, in a change of how the data is organized. We had an example in Pillar 1 that the HPC simulations were generating each of them columns of data. And each of these columns were stored in a different node in the HPC system. But when we wanted to do the analysis with this leaf, we were doing an SVT, collecting all this data. We need the data in blocks. Building a matrix with all these columns and then having the data in blocks, not the square, but blocks. So if we have to ask the programmer to develop this data transformation, it will take time. Maybe it will not be an expert and will be errors. So we said, can we build a mechanism so somebody can provide libraries that implement these data transformations and then a mechanism to invoke them in a more automatically way. So this is the idea. And the other idea is a method to be able to invoke different types of software that may have different type of characteristics without complicating a lot the interface. No? So we defined these two annotations, that software annotation and the data transformation, that tries to simplify for a little bit the life of the programmer. The software invocation is an extension of the task annotation. No? We have seen before the task annotation that looked really simple. But when you have to invoke an external binary, in this case an MPI, things start to get complicated because you have to add the MPI annotation, and it can have a large number of parameters. No? And really the code starts to look a little bit odd. No? But after all, maybe the user don't know exactly these parameters. No? Maybe this is an admin or an expert user that can define these parameters as a JSON file, and then this can be reused in other occasions. No? So this was a little bit what we did. No? If you want to use this software, which is an API, we recommend you to use this configuration, no? And this can be then stored in the software catalog and available to new users that want to execute other workflows that use this work, this API software. No? So this is the part of that software. Then at execution time, what it happens is that the runtime would generate the corresponding commands, no, automatically that implement this, no, for example, the number of threads that are used or the number of processes, whatever. No? So we will interpret this in configuration in order to make the execution correct. And the other aspect of the data transformation, for this I have to recognize that we have not been able to find many different options. We still think that is a very good idea, but we need to explore more use cases. No? This one implements the one that I was telling you, no? The fact that we have data in columns and we want blocks. No? And for example, we have this method that is provided, in this case in the dislib, that is able to reorganize the data in different block sizes. No? After all, a column is a block size pattern. No? So you can change, annotating here with this DT, okay? It says, okay, apply this data transformation to this data structure, and apply this method, .blocks return, and with these parameters, in this case, is the actual shape that you want after the execution. And in this case, this .blocks return is itself a PyComs application, okay, that generates some tasks automatically before the execution of the actual method. No? And everything is managed then by PyCom. You can have this, or in this case is a PyCom's code, but it could be that not necessarily has to be. In this case, is indicated by, sorry, this where it says this workflow equal true. This means that this log-free chunk internally has tasks. Okay, it's in a different way if not. Okay, then another part that I wanted to present is the DSLIP. The DSLIP is a machine learning library that follows a bit the scikit-learn interface. I guess some of you know what is scikit-learn. It's a library for machine learning. It's developed by INRIA, maintained by them and other contributors, very well known, and provides this very simple interface that you instantiate a class. You can do the training with a fit method, and then you can predict on other data. In this case, we maintain this fit and predict interface, okay, but we extend it by the use of a distributed data structure. So then I will show it a little bit how it is, but by means of this, and by means that parallelizing internally with PyComps the fit and predict methods of the different classes, we have parallelized internally application with PyComps, but that looks for the end user as a serial sequential code. Here, really, the effort for the developer is very low. No? And we don't support deep learning, but we have multiple methods for the data management, and also for clustering, classification, model selection with the grid search, random search, other type of these methods. Okay. And the distributed data write basically is implemented on top of NumPy, which is a data structure for Python. No? So each of the blocks, what we do is that we the matrix of the data that will have n samples and a number of features, we define the notion of block size, okay, of block, and basically what we have is that all this data is decomposed into these blocks, which can be stored in an individual node. This does not mean that you need as many nodes as blocks will have the feature. You can have a single node, but what is important is that at the time, the methods will operate with one block in memory. So this enables for large memory problems, because at a given moment you will only need to fit in memory a block or a set of blocks depending on the operation. And we offer also methods for loading, for indexing, etc. of these. And as an example of application that we have developed in this week, just to show a recent result that has been presented last week in the Europar conference, is an implementation of the random forest. In this case, using also the task nesting feature that I was mentioning before, that enables to have tasks inside other tasks. So in this case, this random forest was designed to get better scalability that we had in fact another method before that was not running that well. And we did two new implementations, one based on traditional PyComps and using the fault tolerance method and annotation to find out when the thresholds on the search in the tree were achieved, and being able to cut the nodes of the tree. No? And this was the sorry, I forgot to add the legend. Oh, here is it. So by PyComps we mean this new version that we built. Okay, this is time again, and these are number of nodes. And then we did this nesting version that scales even a little bit better. Okay, this was, for example, running this case with a Higgs dataset that has 11 million instances with 28 attributes. And in this case, the nodes are Mare Nostrum 4 nodes that each of them have 48 cores each. No? And this is a strong scaling experiment where we are using the same data set for all the executions. So you will expect a reduction on time. And we were comparing with MLLib, which is the machine learning library for Spark, with one of the one on the random forest method that is available, which we could see our experience was that was not scaling, neither for strong scaling, neither with quick scaling. No? With quick scaling, what we do is that we have here, if it's with one node, we will have a data size of one side, here doubling 4 times, etc. So that the data size is increasing every time, and you expect to get a flat execution time, now that the time should be more or less the same. With nesting, is quite flat, not totally flat. With the first implementation we did, still when we were passing from 8 to existing nodes, we have here a significant increase. But also with MLlib, even we were playing with different parameters of the MLlib, we could not improve that. And another aspect of that is available on top of PyCom, or PyCom environment, is the distributed data set. The distributed data set is an implementation of the RDD Spark interface, but on top of PyCom. We are mimicking the syntax. In this case, instead of RDD, we call it DDS. Okay, but if you look at the methods, in this case, it's a word count. It looks, for those not familiar with Spark, you will see that the syntax is basically the same. Okay, but then you can implement the same method with PyCom, no? And it will look like this with tasks. Okay. So this is just for comparison of how it will look, the implementation of the word count with PyCom, where you will have task defines, okay, and then a sequential code, or how it will look with an RDD-oriented syntax, in this case implemented with DDS. But the nice thing is that using this implementation on top of PyCom, you can combine both things. You can have parts of the code that are implemented with the DCDS and data sets, but other parts that are used with traditional tasks in PyCom. No? And this will generate a whole task graph of the 2 different parts that are dealt by the PyCom runtime, okay, and executed as a whole in the computing infrastructure. We did a first naive version for each of the different transformations or operations. A set of tasks were generated, but since executing tasks have some overhead because it requires invocation, generation of the task, invocation, so on. So we have done an optimized version where we combine parts of the data. For example, for each of the load data, we are not generating a task, an geometric task anymore. No? We combine this loading with the next transformation that is invoked, or we are combining multiple transformations that operate on the same data as a single task, no? For example. And then we get a more compact task graph, okay, compared to this one, which is more efficient. And for example, here an example of an application that has 2 things is it's an example that we designed it to play. No? Maybe we can think of real examples that may have these different parts. But basically what it was doing is analyzing large number of input text files using dictionaries or other sources of text files, okay? And first implementing with the DDS, no, the Spark-like thing, some methods that were listing the different words and their frequency, okay? And then the second part, the idea was to find clusters of these words to find similarity between the files. Connecting a cluster, if different files are in a cluster, will mean that they have similar words or similar word segments. No? So basically, this will be the main program, and we have this DDS part, and these parts are invoking tasks. I put it separately. No, the count locally is a task, for example. We have it here at the beginning, count locally. Partial cluster. This implements a k-means. Okay, is implemented as a k-means, okay, which is invoking multiple of these methods as tasks. Okay. And this will be for a small data set. This is the task graph that is generated, where we have some tasks at the beginning that process the DDS part, and then these others are the tasks that we have for the rest of the workflow. And at execution, here in this case, the different parts are very well differentiated because we have this node here that we cannot open more parallelism master, but there could be other applications where the 2 type of tasks could be more merged. No? So this is the other type of tool we have, no? That we can execute an application, and generate this post-mortem information. We have actual information of the duration of the task, and you can also get more information like the data that is transferred between nodes, the amount of data that is used. And this case, this was run in Mare Nostrum with one master node and 4 working nodes, each of them with 48 cores. Well, with this, I'm finishing my talk. I hope it was okay, the length. It was a bit tricky with all the introductions. So a bit the conclusion, no, from our side, what we think is that the users, no, there is a demand from the scientific community in general, from applications developers, to have tools that enable this composition of traditional computational workflows with data analytics or AI. People is looking into it every time more, and this makes the applications every time more complex. But also we have that the infrastructures are every time more complex, not only because HPC systems are every time more complex or that architectures are every time more complex, it's because also we want to deal with this integration of IoT devices, different data sources, different raspberries, whatever. So we believe that having models that a lot of them come from the cloud area, like functions as a service or type of these paradigms, can simplify the deployment and execution of applications. And also the fact, this exercise of organizing a little bit the architecture and designing, maybe it's not needed to have as many repositories or catalogs as we have. Maybe we could have designed a single one, but it's important to offer tools that help for the reuse and reproducibility. We really believe on this as well. And well, in general, you have seen that PyComs, although it was thought at the beginning more as an HPC environment for the development of applications, we have been working on different aspects that help on enabling the convergence of these different areas. And we have these other tools that we think also are interesting tools built on top of them, the sleep and the release. Well, finally, I added this slide about all the partners that are in the projects, just to recognize that this, the last part, as I said, is mainly from our group, but in the rest of the project, we have 16 partners with different expertise. This is another thing. Trying to work with people that has a very different background is not that easy, and you need to have some steps until you have a common vocabulary. But it's been very interesting, and we are very happy. Thank you very much.
Thank you very much, Rosa, for this very interesting talk. And now we have some time for questions. So if any of you has something to ask.
Nobody. I have 3 questions, but I will ask one, and then we will see if there are more questions from the audience. HPC is totally not my area of expertise, but I found one aspect, one problem that is similar, that was similar, still is similar with the data integration processes. You presented this graph of tasks, and then it can be executed optimally, suboptimally, or unoptimally, and then what you apply is parallel processing. And in my area, the problem is the same. We have data integration flows, and then people try to reorder tasks to improve, potentially to improve their performance. Is it relevant, that technique in your area as well?
Yeah, it can be very relevant if possible. Not all
because
cases.
this is exponential. All the possible rescheduling is exponential.
For this, you will need to be able to define if the task can be commutative.
Exactly.
We have a schema that tries to address this, because for a set of tasks that have a dependence between them, like imagine you do a matrix multiplication, you accumulate on a block, and you do first block of A by first block of B, here, and then second block and second block. this creates a series of tasks, no? That one run after the other, but in fact, they are commutative between them. No? And there are scenarios when maybe in a matrix multiplication, no, but in other scenarios may happen that with a similar thing, you have data that comes maybe earlier, no? And you would like to change the order because as soon as I have a data available, I'm going to operate it and I speed up my process. And then we offer this commutative operator, no? But I'm saying that it's commutative and then the runtime knows how to deal with it. The other option we have is that we say that are concurrent between them, but they cannot be executed all at the time because for whatever, because they are accessing, like you want to implement a blocking mechanism and you don't want two tasks to access at the same time. So you can define a set of tasks as concurrent, but not all at the time. No? And then the runtime has to deal. But what would be interesting is to extend other patterns, but to find them automatic. The problem is you said that you reshuffle tasks, no? But how you know if they can be reshuffled? In my case, in principle, if I don't have somebody that tell me it doesn't matter if you change this order, I cannot decide to this because maybe I will lead into an incorrect. So we will need to know this information, and once we have this information that maybe doesn't apply in all cases, implementing this type of optimizations really can be interesting. Other thing that I've seen people that have been doing, we have done a little bit in the DDS, but not always, is making coarser tasks, no? Grouping multiple tasks to optimize the execution. This, I don't know if this is something that you have looked at.
Well, they consider the same thing as problem. Oh, thank you. Oh, there are questions.
I think you raised the hand first.
So in if developing like an extension that abstracts certain concepts from parallel computing, yeah? First question, is this going to lead towards some kind of like a standard? Or is there a standard? And the second question is how many such abstractions have we got? We don't know, because you've got under control. If someone's coming into this environment to learn it, how hard, how many abstractions basically are there, and what is the development in those abstractions that you're doing?
Well, okay. For the second part, maybe I will answer the first question, and then I'll try to see if I understood the question. With regard to standards, there is on the area of more HPC, pure HPC, the task-based programming model has been kind of standardized in the OpenMP, which is not officially standard, but is, let's say, it's a pseudo standard because vendors implement libraries of OpenMP. And ESC was one of the contributors to push this task and later task with dependencies into a standard. What we don't have it is in PyComs. I think Intel was trying to push this. I wanted to follow it a little bit, but time's limited. But it would be good to try to push this into a standard for Python as well. Yeah. And then with regard to abstractions, I'm not sure I understood you. So by abstraction, you mean, for example, the abstraction of the tasks, or?
Yeah.
Okay, we have the task is an abstraction. And then the question was about.
How many, more or less, how complex it is to understand the model? If someone doesn't
know the model. Maybe Oscar help with this.
How many different annotations are there?
In the programming model, we have the task annotation, and then the constraint annotation that's on top of the task to give a particular request. Then we have, for example, the MPI and the binary that is more generic than the MPI. And I think that's the container part. So let's say as annotations, 5, 6 at most. Then we have a small interface API for synchronization, the comms barrier that waits for all tasks to finish, and the comms wait on that waits for a value, a data to be a specific data to be generated. I guess I answered.
Yeah, thank you. That's good.
Sorry. we have I cannot show it now, but if you search for comms with 2S and, for example, documentation, we have online documentation in the website that you can check. Okay, and if not, we can speak a little more later. Thank you. And then, yes.
So first, I understood from the previous discussion with Robert, so the tasks, you have to specify the use case and specify whether they can be sequentially or can be parallel. So not that the system, you can obviously specify constraints and then the system automatically generates parallelism or sequential.
No.
That's the first question. The second one is
but this is a question.
Okay, yeah.
It's not that. Sorry, I was talking a special set of tasks that you can define these different, like that there are commutative, or a group that is concurrent, but that you only want one at a time. But by default, the parallelism is extracted by the morphology of the graph. So what we detect automatically the data dependencies between tasks, given the input or outputs that are defined in the annotations. And with this, then we see the morphology of the graph, and we decide which task. Basically, when a task doesn't have outstanding dependencies, it can be executed.
Okay, thanks for this clarification. Second question. So what is a good task size? I mean, the user specified that. So,
good
and
question.
what is the impact on the performance? And maybe some hints how to design a good task. I assume that is done by the programmer or developer.
It's a good question. So by default, if you can, there is a trade-off between the parallelism and the size of the task. No? If you do smaller tasks, you will have more parallelism, but there is also an overhead of the task, or task creation, task evocation, and so on. But there is also, you cannot say, okay, in fact, if I have tons of tasks, I will make them coarser, no? But then you have the limitation of the hardware, because at least need to fit on a node. No? You need the memory of the node to fit your task. We have been doing this basically by hand, no? Like in first version, generated task graph, oh, this is very inefficient, how can I improve it? Now we are working with some colleagues, for example, for the dislip that has this block size parameter, to have some automatic methods based on machine learning to predict what can be an optimal block size, no, data size for your problem. But still, we are not, with the first solution, we are not very, so here is a room for research, very interesting area to work, to help on the developers and the execution. No? Because the program can be correct, but because you are defining the wrong data size, it has a big impact in performance. Thank you. And I think Genoveva.
Yes, thank you. I'm interested in the edge to back end sequencing, particularly when you work with things. Flexibility is very important, because particularly when you're dealing with data, then you have to decide whether to move from the edge, for example, to the high performance layer, and then transferring data can be hard. Whereas in the compilation approach, you are like hard coding, if I understand, many of the decisions that should be done at runtime. And so how do you balance the fact that at some point some resources will be available, and then you want to put data, for example, from the edge to the backend, etc. And whereas you have a already compiled decision made on how the whole process will work.
In this area, we have been working a little bit as a separate thread. In fact, there is a flavor of the runtime that is a little bit different. It's agent-based. The agent is the implementation, but basically what we have is that it's also, instead of being centralized, as what I show, is distributed. And then every time you deploy a node that runs comms, you have the master and the worker on it. So each of the nodes can become a master and a worker. Now, this is already giving some flexibility because it has more, can make more better decisions, no, in the node. And the other thing, we are adding new ways of execution in these more flexible environments. The nodes peer between them, in principle with those that are closer to execute a sub workflow. No? And we have been working on more advanced scheduling policies based on, we did an experiment with wave theory or other type of schedulers. In fact, we want to continue this because it was done by an undergraduate student. But on these areas, there is a lot of research that is open also, and it identifies very well. Yeah. Thank you. I think all guys were.
Well, we don't have more time now because there is a coffee break and then the next session and so on. So thank you again.